All right, it seems to be time to start. Can everyone hear me?
Yeah.
All right. Okay, so before we begin, I just want to remind you guys to fill out the anonymous survey. Um, so it seems like none of you from this discussion session have filled it out yet, or at least only one person. So um, it would be nice if we can get some feedback on all that stuff. All right. Any questions about general things before I get started today? No? Okay. All right. I will get started. So today we are going to just discuss two of the past lectures, which are regarding MOS transistors, CMOS gates, and inverters. Okay. So transistors, right? Transistors, in our case, we have MOS transistors. Do you know what MOS stands for? Anyone? What does MOS stand for? Okay. It stands for metal oxide semiconductor. And this actually has to do with the structure of the um, MOS transistor. So if we actually look at this, structure diagram here, what we actually have is a sandwich of a gate, which is the metal. But I will let you know that the gate is actually not made of metal most of the time now. In fact, actually, no, I will take that back. It was made of metal in the beginning. In very old technologies, it was made of aluminum. And then they switched to polysilicon because that generated lower threshold voltages. And then now they're actually going back to metal, but it's like more advanced metals like niobium or tantalum or something. But anyway, you have the gate metal, and then you have this oxide layer here, right? And then underneath you have semiconductor, which is silicon, and the silicon is doped with ions to be so-called N-type or P-type, which means that they have more positive ions or more electrons in their crystalline structure. All right. So for MOS transistors, we have four terminals, right? We have the source, the drain, the gate, and the body. Most of the time, we are only concerned about the source, drain, and gate, but the body does affect it when you start, considering some like higher level or secondary parasitics, or if you want to actually control the transistor also through the body. There are ways that you can change the threshold voltage and other stuff. That stuff you'll learn, if you take 141 or whatnot. So for an NMOS transistor, we essentially have three general modes of operation in the classical MOS transistor case. Cutoff, which basically equals off, right, when the transistor is not supposed to conduct current. Um, this mode of operation is defined as the voltage of gate to source is less than the threshold voltage. Okay. And then the next region of operation is triode or linear. And this is sort of like a variable resistor. And the variable resistor is controlled by the drain to source voltage. And in this case, it has to be on, which means VGS is greater than the threshold voltage. But the amount of resistance that you get is proportional to what VGS is, as long as it is less than the VGS minus VD V threshold, which is also sometimes referred to as VD sat or V drain saturation. Okay. And then the transition between triode and linear region is at that saturation voltage for the drain. And in saturation, you can see that this is greater than or equal to VD sat. Okay. So what about PMOS? How are these voltages different for a PMOS? Anyone want to take a guess? All right, for PMOS, you generally use absolute value. So for example, cutoff for a PMOS is where the absolute value of VGS is less than the absolute value of V threshold for a PMOS. Okay. And then MOS transistors have a lot of parasitics. So let's take a look at this diagram to the bottom right. can people just tell me what parasitics there are, and I'll annotate them in this diagram as we go.
We have like a modeled output capacitance, right?
Sure, but I want to talk about parasitics that are intrinsic to the transistor itself.
Isn't there one between like the L region and like N plus? N
Yes,
plus?
right. So for each n plus, there's one here, and this one is going to be like C drain to body,
Hmm.
and then from here you'll have a C source to body. Okay. What else?
Is there one between the gate and source?
That's correct. So this is going to be C gate to source. And then correspondingly, you have one C gate to drain, right? What else? Okay, you also have a parasitic capacitance between the drain and source. This is usually, not very large. And then you also have one directly from the gate to the body. Okay. Now, for transistors in saturation region, a lot of times the predominant capacitance that you see looking into the gate is actually going to be the gate to source capacitance. But the gate to drain capacitance is also important because it's sort of like a feedback in most cases. And that will degrade the performance of your transistor because the transistor is essentially fighting against the current that you're injecting into the gate. Okay. So, for the purposes of the class, you don't really need to know about all these parasitic capacitances. For the most part, we're going to just, think about a simplified capacitance model where, you just have this VGS, right? And then you have some like parasitic capacitance here. And yeah, and then you have, the input capacitance that you see equal to that, predominant gate capacitance and the parasitic capacitance here. So you have a C in here. Okay, and then one other thing that I think was addressed in class was over the years we have transitioned from planar bulk CMOS, which is the structure that you see in this diagram, to FinFETs, right? So what was the move to FinFETs? What did it do for us? What were some of the things that FinFET did for us? Okay, for one, we had like better gate control, right? Because the the gate is sort of wrapped around the semiconductor that houses the channel, right? And then the other one is improved process scaling. Because with this transition into the third dimension, we can decrease the channel length even more and make all of our feature sizes even smaller. All right, any questions here? Okay, moving on. So MOS transistors, we think about it as a non-ideal switch, okay? So there are two, equivalent resistances that you can think about in a MOS transistor. One is going to be the on resistance and the off resistance. And in a good MOS transistor, the on resistance has to be much less than the off resistance, but neither of them are going to be truly zero or infinite, okay? So basically, this MOS transistor that we see on the right corresponds to this ideal switch, where the switch closes when you, exit cutoff, right? Oops, sorry. Right, and then you have a equivalent on resistance. So what does it look like when the transistor is off? What is our equivalent diagram here? Equivalent diagram is going to be, a source, and then you have an open switch, right? But then you're going to have a parallel resistance, which is going to be R off. Okay. So the transistor will always be able to sink some amount of current, regardless of whether it is off, where the transistor is in cutoff region. Okay. Now for an NMOS, the source terminal of the NMOS should always be at a lower voltage than the gate or the drain, and that's what defines the NMOS being able to conduct current from drain to source. And the NMOS transistor, what you need to know is that it is ideal for passing a low voltage, which is 0 or the ground supply. Whereas the PMOS is opposite. The source of the PMOS has to be higher voltage, and it is ideal for passing ones or the VDD supply. Okay. Now, in these diagrams, it's important to note that the source node isn't actually, physically one's the source and one is the drain. What defines the source is actually depending on the voltage. Because if we go back to this diagram on the right, the planar CMOS or planar NMOS transistor actually has physically the same structure for the source and the drain here. So if you were to apply a lower voltage on the right side versus the left, then the right side becomes the source. Okay. Does it make sense? Okay. Moving on then. All right. So let's analyze these switches. Okay. And basically, let's go one by one and see what happens to the transistor and evaluate why these say they are good zeros, bad ones, good ones, and bad zero. Okay. So in the first example, what we're doing is we're actually doing a step transition up to VDD. Okay. What does the output voltage look like here? Right. If we have some on resistance, we are going from VDD down to 0 in some sort of exponential thing, right? We have some RC time constant that is generated from this R on and then capacitance. Now, in this case, what is VGS? VGS is always equal to VDD because the source is grounded, right? What does this mean? This VDD is greater than VGS, is greater than V threshold, which means that this transistor is constantly on, okay? And also has the same resistance all the time. So this means that the output is going to be pulled to 0 eventually until the output capacitor is completely discharged and the drain to source voltage becomes 0. At that time, it is indistinguishable which way the current would flow because neither the drain or the source voltage is different from each other. Okay. Now let's take a look at this NMOS in the second example, right? Again, we're having a step voltage on the input, but this is supposedly a bad one, right? So what we're trying to do is we're trying to pull the output node from a 0 high, okay? And so we're trying to go something like this. But the question is what happens, right? In this case, VGS is not constant, okay? It's going to be equal to, what is it? VDD minus whatever the V source is, right? Or V output, okay? And V output is changing, right? And do you know whether it is greater than V threshold, right? We don't, it's not greater than V threshold when the output becomes VDD minus V threshold, right? And so at that point, no more current can be sunk through the transistor, and then the output voltage flattens here at VDD minus V threshold. Okay, so the rationale for this is that the VGS is not constant. What this means is that the switch turns from on to off over time. All right, and it is off at V gate equals, off at V source equals VDD minus V threshold. Okay, and that means that the output is only pulled to that value. Now let's take a look at this PMOS and see how it passes a good one, right? So let's say we go from VDD down to 0 here, and we try to pull this output to up, okay? So in this case, we have another exponential going up, right? Have a R on for PMOS, okay? And this voltage ends up being VDD. Why? Because VGS, in this case, is always equal to negative VDD, which is always less than V threshold P, okay? Or you can think of it as absolute value of VGS is plus, which is greater than absolute value of V threshold P. And so that means that, again, this is constant on, right? And output goes to VDD eventually. And then similarly, for a PMOS trying to pull to 0, right? This again coming down, this voltage characteristic would look like this, where this value is going to be absolute value of absolute value of 3 threshold P. Why is that? Again, because absolute value of VGS is equal to VDD minus V out, right? And so VGS is not constant, just like example 2. Okay, make sense?
I'm a little confused by this. So is it due to the I mean, it makes sense to me from the perspective of looking at the capacitor. Like, the capacitor is going to make it such that, like you said, VGS is not constant. And that makes sense because, like, of the scenario, like the capacitor is always going to be, like you said, in the good scenarios, it's at the drain, and in the bad scenarios, it's at the source. So is that why I'm not understanding this other reason as to why the VGS equals VDD minus V out? Like, I understand that, but I don't see why that specifically leads to it being bad. It makes more sense to me in terms of just the capacitor. Or
Okay,
maybe
so
I'm misunderstanding.
Basically, let's take a look at the example number 2, right? This transistor is acting as something that can push current onto the output capacitor.
Okay.
Right? So when the output voltage is 0, right, this capacitor can accept current through the transistor from VDD, sort of this path, right?
Right.
Okay, so when the output is 0, this transistor is on. You can see that, right? Because VGS is going to be VDD minus 0.
Sure, yeah.
Okay.
Makes sense.
Now, as the current flows into the capacitor's voltage has to increase.
Right.
Right? And so the effective VGS is going to be now VDD minus the output voltage, whatever that output voltage ends up being.
Okay, yeah, sure.
Yeah, and the transistor will remain on until the output voltage becomes this value, at which point the VGS is less than V threshold and the transistor turns off.
Okay. Yeah, okay, that makes sense.
Yeah, okay. So therefore, this transistor in this configuration would never be able to pull the output capacitor all the way to VDD because it has turned off before that output voltage has reached VDD.
I see. So it's not even like it's less efficient. It's literally like it won't work almost.
It won't work. Yeah, the switch will turn off before it even gets
I
there.
see. Okay, that makes sense. Thank you.
Obviously, if you go into like higher order models, this is not just a single switch, and you're talking about like leakages and resistances, but that's beyond the scope of this class.
Thank you.
So in that example, will it oscillate between on and off, like very fast, and then just stay at that V out equals VDD minus V threshold?
I mean,
for forever, I
not
guess.
oscillate, because there's no way that the output voltage can come back down from this level, right? From this level. Unless you're talking about some like leakage current going through the capacitor, then that would be a different story.
Oh, so when it's off, does it just look like a open circuit then?
Yeah, it's an open circuit, and you just have a floating capacitor.
Okay, okay.
Yeah.
Yeah, good point. Mhm.
Yeah, and a floating capacitor absent any leakage would just keep its voltage.
Mhm.
Yeah. Okay. All right. So if this makes sense, we just want to tell you that for transistors in this class, you mostly just need to know the following things. The MOS switch model, especially also the conditions for, on and off, right? So this is the difference between cutoff and then linear or saturation region. The on resistance of a transistor is proportional to the length and the width of the transistor. Okay, so the R on is proportional to some like resistance thing, resistance constant times the L over the thickness and the width of the transistor, which, this whole thing is proportional to L over W. Okay. The difference between NMOS and PMOS, as we already discussed, is just the, flipping of the voltages that you see on the gate, source, and drain. Knowing that NMOSs pass good zeros and PMOSs pass good ones, and then the simplified parasitic capacitance model that we just discussed before. Basically, in the lecture slides, you'll see some equations, but for the most part, you just want to know that the parasitic capacitance is going to be proportional to some constant times the input capacitance that you see going to the transistor. Okay. So yeah, that's pretty much it for transistors. And so let's do some examples for how to make some logic out of transistors. So can someone tell me what the output F is as a function of A and B? So assume that you have these 4 signals available to you. Okay. How do we do this? Anyone have an idea for how we would solve this? So again, these transistors, right? We're considering them as switches. So these are NMOS switches. So these switches turn on when the gate is 1. Okay. So what does that mean? This particular switch turns on when A equals 1. So knowing that, how would we construct F from this diagram?
So you can tell that if the transistors are in parallel, then they're going to be ORed together, and if they're in
That's right.
series, they're going to be ANDed together.
Okay. All right, that's true. Okay, so why don't we do this path by path? How do we do it? Let's start with R1. How does R1 get from here to the output?
If A and B are both 1.
Yes. Okay, so it takes this path, right, to the output. Right, so that means R1, A, and B. Okay. Then how does R2 get to the output? This is
Yeah,
going to be
just
4
not
because
A, B.
it's parallel. Yeah, that's right. R2, not A and B. And then we can do the same thing for R3. This will be A and not B. And then R4, not A and not B. Okay. So that's how you would construct the switch logic for this diagram here. Now, what is this essentially doing? What is the structure of this gate?
Would it just be on whatever works?
Say that again.
It will be on no matter what, right?
Is that true?
Yes.
Okay. Right, because any combination of A and B will give you one path that is on, right?
And only one path.
And only one path. So what is the function of this gate, if that's the case?
Just one, right? I think
Or
it's
like
one.
Isn't this almost a
if
mux?
this circuit, yeah, that's it. If this circuit were a logic gate, this would actually be a 4-input mux.
Let's go.
Yeah. right? Where the inputs are R1, R2, R3, and R4, and then the mux control pins are A and B. Those would be the 2 bits of the control. Very good. So now, given this circuit, can you find any issue with implementing a 4-input mux this way?
Well, since it's all like PMOS, right? So it's possible that we'll produce like back 0 or like back good. I don't remember the other one, but like PMOS, I think only good for one other.
Yeah. Okay, you're on the right track, but these are actually NMOSs. You would be able to see that they're PMOSs if there was a little circle on the gate.
Okay, yeah.
Yeah, so these are
So if the R's were
NMOSs.
high, so like if
Uh,
R1, for instance, was high and then A and B were
correct.
high, that
Yeah.
would be the scenario where it would probably not produce a very good 1 out to F.
Correct.
But then I think, so zeros though would probably be fine.
Zeros would be fine.
If
You're right.
R1 through R4 were 0.
That's right, yes. Okay, so how would we fix this then?
Probably like in lecture, they talked about the pull up versus pull down network.
Yes,
that
that's one way of doing
kind of
it.
along
But
that
what if we
track?
just wanted to like do a small modification to this and put something in parallel with these switches? Okay, so what passes good ones, right? PMOSs, is that true?
Yeah.
Okay, so what do we do? We put PMOS in parallel with the NMOS. Oops. No. Okay, so what it looks like is you're going to put a PMOS transistor here. And then what does the connection here need to be? Instead of not B, it has to be the complement of not B. So this would just be B. Do you see how that's the case? As in, this entire structure here is on when B equals 0, then not B equals 1. And it's this switch here would be off in the opposite case, right? And so what is this called? This is actually called a transmission gate. Do you see how does this make sense?
So what's the difference between using a transmission gate versus doing the complementary MOS logic with the pull up, pull down?
So again, this is a switch logic. This is not CMOS logic. So switch logic is where you have some inputs and you're using switches to generate a path to an output. CMOS logic is a little bit different, and we're going to go into that next.
Okay.
Yeah, and in this case, switch logic, the reason why we want to use transmission gates is because, right, when the input is a 0, we can pass a good 0 using the NMOS transistor in the transmission gate. And then when the input is a 1, we can pass a good 1 using the PMOS transistor in the transmission gate. So this switch as a whole, when you put an NMOS in parallel with a PMOS, is able to pass both a good 1 and a good 0.
Maybe I'm getting a little ahead, but are there like power differences between using like switch logic and then versus connecting everything to the rails and having like CMOS logic?
Absolutely. So let's put it this way. What is the thing that would drive current? Let's say, right, on output, you're going to have some sort of load capacitance here, okay? Right? And in order to change the voltage on F, you have to pull or push current into this load capacitor. So where would the current sources be in this logic gate?
Here it's R1, R2, R3.
That's right, yeah. You would have current sources that connect to here, right? But then these transistors in this gate effectively are all passive, right? They don't essentially draw current by themselves, only parasitic capacitances and whatnot. So, you're essentially having a path through switches to the output, and the power is being drawn by the gate that drives this whole logic gate. Whereas for CMOS logic, you'll see that the gate itself, the CMOS logic, will draw current because it actually draws current from the supply and dumps it into ground, depending on what the output needs to be. that make sense?
Okay. Yeah, I
Yeah.
got it. Thank you.
So now, yeah, we're moving on to CMOS logic. And what does CMOS stand for? Anyone know? What does the C in CMOS stand for?
Complementary.
Yeah, that's right. Complementary. Okay, and complementary MOS logic mostly implements inverting logic functions. Okay, and you're going to have in CMOS logic something that looks like a pull-up network and a pull-down network controlled by the same thing, and then they both are connected to the same output. All right, and the key to designing the pull-up and pull-down network in a CMOS gate is the fact that they are dual. And dual means that you can translate from one to the other using De Morgan's law. All right. So in order to build the schematic of a CMOS logic gate, this would be a general flow for how you would do it. So given, let's say, an output that is a logic function of an input or multiple inputs, right? What you would do is you would need to simplify the logic function first. And what you want to target is a function that kind of looks like out equals not of some large expression. And the reason why we want to do this is because we want to start from the pull down network. So everything in this expression here under the not becomes what you build for the pull down network. All right. And the pull down network is all comprised of NMOS transistors. So once you do the pull down network, you can find the corresponding pull up network. And the key to doing this is that anything that is in parallel in the pull down network becomes serial in the pull up network. And then anything that was serial in the pull down network becomes parallel in the pull up network. All right. And then after you build the schematic of the transistors that corresponds to both the pull down and the pull up network, then you get towards finding the size of the transistors. And the way you do this is you first size the so-called critical path, which means the path through the maximum number of transistors in either the pull down or the pull up network. And then after you find the size of those transistors, you can find the size of the other transistors that may be in parallel with the critical path. We'll go into some examples for how to do this through the rest of this discussion. So let's take the example of an XOR, right? And XOR is going to be like Y equals A XOR B. And what we want to do is construct the CMOS logic gate for an XOR and assume that you have A bar, B, and B bar available to you as inputs. So how would we start constructing this? Okay. Right. What is A XOR B equal to? In something that might be constructed of ORs and ANDs. What would this be? A hint? A.
It's I think you can do A and not B, or not A and B.
Perfect. Okay, but this expression by itself is not amenable to generating CMOS logic gate, right? Like it's not very clear how you would design the pull down and the pull up network from this expression. Okay, so let's walk through it step by step. The first thing you need to do is you need to put a knot on top of this whole thing. So let's start by actually putting two knots, okay? Because a knot and a knot negates itself, right? So we have not, the expression A not B, or not A and B. So where do we go from here? Let's apply some De Morgan's laws, right? What would be the first De Morgan's law that we might want to apply?
The A not B term. So we would simplify the addition.
Yes, right. So you want to take this part of it, right? And the De Morgan's law would be something like this, right? Equals
Not x times not y.
Right.
Yeah.
okay. So what does this become?
So that would be not over a b not, which we could simplify more, but I guess we'll skip that for now. Plus not over, or times not over a. Yeah, a not b.
Okay, great. Now, how do we simplify this even more? What De Morgan's law would we apply here? The other one, right?
Yeah. Make it addition.
Yep.
So then a plus.
Okay. So what does this become?
So a plus, or not a plus b, if you simplify it a little bit. And then the other term is a plus not b.
Great. Okay, and then from here, we can just distribute this. Okay?
Right.
Right. And what do we get from this expression?
So not a and a would be 0.
Yeah, not a and a would be 0, so let's leave
Not
it out.
b, so they'd be ba and then not a, not b.
Okay, right.
Yeah, I did not over the whole thing. Yeah.
Right. Okay, so now what we see is that we have a not over the whole thing, and this expression in here, right, becomes something that we can build a pull-down network out of. Okay, so how do we construct that? Let's say we have a y here. How would we construct the pull-down network?
Parallel the two
Okay.
MOS with
Yes.
four MOS
Okay.
parallel for with 2 in series.
So two pairs
2 pairs of
of
series
2
MOS.
in series, right? Good.
And,
All right. So right. So this is what you're saying. So
Yeah.
what goes here? What goes on the gates? What about the first one?
AB, so the
Let's
product
look at this
term
one.
to the series.
3, 4. Okay, so what goes in NMOS 1?
And not A,
Okay, not A. How about number 2?
not B, not
Good.
B. AB.
3, yes. Perfect. Okay, now how would we build the pull-up network with this? How many PMOS transistors do we have?
4.
Right. And what configuration would they be in?
One series, 2 pair.
Yeah. One series, 2 parallel. What do you mean by that?
2 pairs of parallels PMOS. How to describe it?
Yeah, like
PMOS.
parallel was in series, right?
In series,
Yeah.
yes.
Okay, all right. So if this is VDD, you're going to have essentially 2 pairs of parallel PMOS, and then you put those in series. Okay? Like that. And then you get the same exact inputs in the same configuration.
I think, no.
Oh, sorry,
The-
I messed up. Yeah, you are correct. You would have
not A,
not A,
not B, B.
yes, not B and B. Yes, you're right. Because the NMOS on the left here, that pair gets parallelized and then put on top. Yeah. In series with the other path on the right. Okay.
Yeah.
Thanks for calling out my mistake. Does this make sense? This kind of flow for how you translate from equation to logic gate?
Is that kind of like very the simplest is like example? Like I mean, we could get a harder in exam and homework as well. I mean, that's
Yeah, you will have some slightly
Harder.
harder ones, like 3 input. But the flow is very similar. You just have to make sure that you generate an equation that looks like this, and then the pull down network becomes relatively easy to design.
Okay.
Okay, so now that we have this, let's go on to something a little more advanced and start doing sizing for this. Okay, so what we want to do, what you always want to make sure when you first read some sizing question is this. It means that in a minimum sized inverter, the width of the PMOS and the width of the NMOS is always equal to 1. What does this actually mean when you have the width equal to each other?
They have the same transition delay from 0 to 1 and 1 to 0.
Okay, but what does that really mean, right? If you think about an inverter sort of like this, R on P.
Resistor,
switch,
the
right?
same
Yeah,
resistor.
the resistors are the same.
Yeah, okay. So let me finish drawing this. Okay, so what this means is that, yeah, R on P equals R on N. All right. So that's very important to figure out when you first do a problem like this.
But
Okay.
didn't the PMOS like, even they have the same size, but the PMOS will have larger resistance
Uh,
or smaller.
No, as in if you are given this equation here, WP equals WN equals 1 in a minimum size inverter, then you can deduce that the resistances are equal. However, what if the PMOS width is 2 and NMOS width is 1 in a minimum size inverter? What would that tell you?
Oh. Yeah, the resistor is bigger for the PMOS because
that's
the
right.
size is bigger.
That's right. Yeah, the resistance would be twice as large for the PMOS in that case.
So the current will be small.
Right.
Okay.
Yeah, that's right. Okay, so let's design this, logic gate, right? What do we have?
Question.
Yeah.
So if the width of PMOS was larger, wouldn't the resistance be smaller because it's proportional to L over W?
So no, what it's saying is that in a minimum sized inverter, the goal of having the minimum sized inverter is for the equivalent resistance of the PMOS equal to that of the NMOS. So for, if you have a PMOS, which is of width 1, that would have twice the amount of resistance as a width 2, right? Based on that.
Oh, yes. Mhm.
Okay, but
Okay.
for a minimum sized inverter, the key is that you always want the pull-up resistance and the pull-down resistance to be the same.
Mhm.
So if the width of the PMOS is 2 and the width of the NMOS is 1, that means that the PMOS, each unit PMOS would have twice the resistance because you need 2 of them in order to have the same resistance as 1 NMOS.
Yeah.
Yeah.
Okay.
Does it make sense?
Yeah.
Okay, great. Okay, so let's construct this logic gate, right? I'll just do it for you. You have A or B and C, right? So it's going to look like this. And then that's ORed with D and E, right? And then the pull-up network here would be BDD. You'd have, let's see, you would have this would be E and D. This would be A, B, and you'd have C here. Okay. So how would we size this, right? The goal is to have a pull down resistance equal to that of the minimum size inverter and a pull up resistance also equal to that of the minimum size inverter. So what is the so-called like critical path through all the transistors here? The critical path being the most number of transistors it takes to go from a supply to the output.
ABD or ABE.
Yeah, that's right. So it'd be this path or this path. Those are the two critical ones, right? So how would we size those transistors? To have the same equivalent resistance as a unit size inverter. What width would we put on these PMOS transistors?
The size W/3.
W over 3. So you're saying you want 1/3 here?
Yeah.
Okay, so if you put 1/3, 1/3, 1/3, what would be the equivalent resistance going through 3 transistors of width 1/3?
Oh,
Yeah, I think you have it backwards. It actually needs to be 3, right? Because, you know, if you have
oh,
width 3 in series, right?
more driving capability. Oh,
You sort
I
of
see.
need
Yeah.
R over 3, R over 3, R over 3, right? In order to be equal to R, right? Make sense?
Yeah, correct. Makes sense.
Yeah. Okay. So therefore, if this D is 3, then E also needs to be 3. Okay. What does C need to be then?
That would have to be so it'd have to result in 2/3, which means it would have to be 3/2.
That's right. What is 3/2? That's 1.5. Okay. All right. And in the interest of time, these are going to be 2, 2, 2, 2. You can work out why that is yourself. All right. Moving on. We need to talk about the static behavior of a CMOS inverter. Okay. So a CMOS inverter, in the most ideal case, would have a 0 P resistance when it is on pulling high and also pulling low in the other case, right? So in the very ideal case, you would actually have a voltage transfer characteristic where VA is here and V out is here of a sharp transition, but that can't happen, right? Because the resistances are finite. So what we see is that the actual voltage transfer curve actually looks like this, okay, where there's a continuous point, and the switching point for the transfer characteristic from the input to the output is determined by these voltages, V input low and V input high. And in a continuous curve like this, it is defined where the slope of the curve is equal to -1 here and here. Okay. And then going from this curve, we sort of define some noise margins. And noise margins are defined by this. And noise margins mean that the, how to say it? The input voltage that would result in a high for the output. Sorry, no. Wait, I'm confusing myself. The input voltage that would result in the output being low has to be above a certain amount from the previous logic gate. And the smaller the noise margins, the less sharp that the voltage transfer curve is. So yeah, so basically if you have a very large noise margin, that means your curve is like very steep. But if you have a very large, this would be large noise margin, and this would be small, your voltage transfer curve would look very shallow. And in general, you want large noise margins because if you have any noise coming from a previous logic gate going into the gate of your inverter, you don't want that to affect the output voltage that you see or the output logic level that you see. So you can tolerate more noise on the input before the output actually seems to switch values. Okay. So I will try to go through this example pretty quickly in the interest of time. But in this question, we are trying to draw the voltage transfer characteristic of this particular inverter with these parameters. So what we see is that we have N resistance and a P resistance, which are slightly different from each other. Okay, and they are supposedly constant for this supply equal to 1 volt. So what does this tell us, right? If we have two different threshold voltages and different on resistances, it means that if we have some sort of situation where the input causes both transistors to be high, we have 3 kilo ohm and 2 kilo ohm. Okay, and we have equal per micron times 1 micron. Okay, if this is 1 volt, what would this output voltage be? This output voltage would actually be 0.4 volts. And you can work that up yourself because this is a resistor divider. Okay, if you have 3 kilo ohms on top and 2 kilo ohms on bottom, this would be what the output voltage is. Okay, and then in the case where one transistor is off, then you'd pull up all the way to VDD or ground. So the voltage transfer characteristic of this particular case is actually a stepwise function, right? And it's going to look like this. When the NMOS is off, which is NMOS, or the A is less than 0.2 volts, the output would be high. And then once this reaches 0.2 volts, this drops down to this level, which is going to be what we determined just now, 0.4 volts. And then when the PMOS turns off at, this would be VDD minus VTHP equals 0.7 volts, then the NMOS pulls the output low, okay? And in this case, this is a stepwise function, and V input high is going to be defined as this voltage, and V input low is this voltage. So your noise margin is going to be V output high is here, V output low is here. So this is going to be 1 minus 0.7 equals 0.3. And then this is going to be 0.2 minus 0, which equals 0.2. Okay. Let's see. I think I might be out of time for anyone who wants to stay on. I'll keep going. I just want to go over, this is going to be the last slide, but CMOS inverter RC delay is something that I guess you'll learn a little bit more as the lectures go on. But what you want to think about is that transistors, or any logic gate rather, in this case an inverter, has an equivalent resistance looking in for pull down and pull up, as we have already discussed. And so what you define is some propagation delays, which are T propagation for high to low, which means the output is transitioning from VDD to 0, and then this one would be the output is transitioning 0 to high. Okay. And in this case, if you have an equivalent resistance, this becomes just an RC time constant, where T propagation of, let's say, high to low is going to be equal to R equivalent N times the output capacitance, which in this case is C parasitic plus C load. All right. And then if you work this out, earlier we saw that C parasitic is equal to gamma C in. So gamma C in plus CL. And then what we can do is factor out the C in to get gamma plus CL over C in. And this value here is defined as a fan out, which is very important when you chain logic gates together. And that's defined as F. All right. So what you'll see a lot is R equivalent C in gamma plus F. And this will be very important as you go through later for determining how the impact of fan out, which is increased number of logic gates on the output, contributes to the delay of the gate. And when you chain multiple gates together, you need to control the amount of fan out that each gate sees to minimize the overall delay through the chain of logic gates. Okay. Yeah, so that's it for this discussion. Any questions? Well, I am 5 minutes over.
So if you had a chain, I guess this is kind of a very quick homework question.
Yeah.
So like in the instance of number 3, when you have a chain, would the only C load you're facing be the input capacitance of the next transistor?
Yeah, that's
Like
right.
it wouldn't be like the result of all of them, because that wouldn't make sense, just because of it's not how the circuit works.
That's correct. Yeah. So, right, if you have, but let's exaggerate this, right? If you have one inverter and then one big inverter here or something, right? The parasitic capacitance is looking in here, and the
Mhm.
load capacitance is looking in there.
So CL, looking from the perspective of the small one, the CL would be equal to the CN of the big one.
Yeah, that's right.
Okay, that makes sense.
And the CP is the parasitic capacitance of itself,
Of itself,
looking
right?
into its drain. Yeah.
Okay, that makes sense. Thank you.
I got confused. What's so you factor CM out here, right?
I factored C in out. Yes, that's right.
What's the purpose we factor that out?
It's just to simplify, or it's just to rearrange this TP equation into a form that you'll see later on, which is this form.
So in that case,
Which means, sorry, I'm just going to continue. The R equivalent C in is going to be sort of the intrinsic time constant of the inverter.
okay.
Yeah. And then anything that modifies the intrinsic time constant inverter is going to be a function of its parasitic capacitance and the fan out.
Wait, so what's CL in over C in here? Like F, the little F. Is that just like define?
Sorry, did you you're saying how did I get from here to here?
No. I know you just factor the C in out, right? I'm
Yeah.
saying that what's CL over C in?
Oh, okay. Yeah, I said that CL over CN is defined as a fan out,
Fan out,
which
is it?
means
Okay.
like if you have C in, right, of a unit sized inverter, okay, and then driving something bigger, looking into here, which is CL, right? Let's say this was of size 3, right? Then this inverter would have CL equal to 3C in.
Okay.
Yeah, and so the fan out is equal to 3 in this case.
Okay.
Yeah.
Is that like some term that we define it somewhere?
Well, I mean, what I'm saying is like this is the definition. So I'm defining it here that CL as seen from an inverter compared to its input capacitance
So
is
all this
defined
will
as a
be
fan out.
all those like will be given like also to the gamma as well, right here.
You're saying it will be given what?
So all this like term will be given, right? So that like little constant here, like the gamma.
Yeah,
that-
that's right. Yeah.
Okay, yeah.
Yeah, these are given. Right. So gamma is actually a technology dependent parameter. And fan out is simply a ratio of what the input capacitance that you see looking in is compared to a unit size inverter.
Okay. Thank you.
I have a question.
Yeah.
Is there no natural log of 2 term in the propagation delay?
Yeah, there is. If you end up like finding what that exponential term is, but just for the purposes of
Okay.
doing
And
this,
for the
it actually, if I really want to be accurate, this is sort of like a time constant, right?
yeah,
So the
okay.
the TP would be
Exponential tau.
ln 2 times tau. Yeah.
Okay, yeah, that makes sense. And for the smaller inverter on the example on the left side,
Yeah.
you said the output capacitance of that one is CP plus CL, right?
Yes.
And the input capacitance of the larger one is just CL.
No. As in the equivalent capacitance that you see here, right, is going to be 2 parallel capacitances here, right? So that's what CP plus CL is equivalent.
And that's defined as the output capacitance of the smaller one?
Of the smaller one, yes. Right.
And so then what we define as the input for the larger one is just CL? Or
That's
is
correct,
it also
yeah.
CP plus CL?
Well, no, as in you're talking about like the capacitance looking in, right? So what you see looking into this guy this way is only CL. But what you see looking out from here includes the previous inverter's capacitance.
Okay, sure.
Yeah.
Okay. Thanks.
Okay. That's
I
it.
I have a question.
Yeah.
So what are we gonna do in today's lab?
What do you mean? What are you going to do in 2 days?
Like so today, so the lab is over, right? Up to lab 6.
Oh, you're talking about
So-
lab now. Okay, let me
Yeah,
end this
labs.
recording. Talk about
Sorry.
lab. Yeah.